continue what, where we stopped last, when was that? It was Sunday. So we were talking about motor behavior. We're talking about how the system actually is using sort of an internal model in order to generate a prediction. And this prediction that is generated by what we call an efferent copy of the motor command or the descending command is used to generate expected sensory feedbacks, or we at least predict what will be the sensory consequences of our movement, and we can continuously compare this to the actual command in one hand and also the late sensory feedback, and in a way we are being able to have a faster control, a more real-time control policy of the motor command, as opposed to a case where we are just relying on external feedback that is very delayed and very late and may lead either to imprecise or inaccurate movement or to some instability at of the plant because of the delay in these negative feedback. So now, I mean, after we kind of discussed the organization of, or at least what we think is the organization of motor behavior, we now going to talk about the implementation, neural implementation of this of the system. And the way we'll talk about it, I assume that you learned about the spinal cord, at least in part, right? Motor neurons, spinal cord, spinal circuitry, reflex pathways. I think Matti already gave you some introduction to that. And then, so I will start with descending pathways. There is some disagreement about what we actually learned, but I think it's I will not rely too much on that pre-existing information. So I'll talk about the descending command, how in the descending pathways, how information from supraspinal structures reach the spinal cord. There are several pathways to do that, and what is the functional implications of each of these pathways. And then I'll mostly talk about the pyramidal tract, which is really the pathways that connect directly from motor cortex to the spinal cord, interneurons and motor neurons in the spinal cord, and that is sort of what we consider to be the infrastructure for voluntary control. Okay, so when we talk about descending pathways, we are talking about a set of pathways that include the corticospinal. You see from the motor cortex, pathway in red, there is vestibulospinal, reticulospinal, rubrospinal, and tectospinal. These are sets of pathways that are connect from midbrain structures, brainstem structures, all the way to the spinal cord. So the system actually, the motor cortex has two ways to reach downstream elements, either direct via the corticospinal and indirect via pathways, because all of these structures are, at least to some extent, under the influence of the motor cortex. So descending pathways are organized in a both hierarchical and parallel manner. Okay, so there is some hierarchy in the descending pathways, but there is also a lot of parallel or redundancy in these pathways that possibly make them more resistant to injury. And the high level of the, such as the motor cortex, have both direct and indirect access to low-level structures. So if we look at the spinal cord, at the spinal level, so this is the gray matter, right? This is sort of the butterfly. And this is the ventral horn, where the motor nuclei are located. And this is the sensory side. And you see that there is a general segregation between medial and lateral systems. And we talk about motor neurons and interneurons that are located in medial position, that they are related to axial and proximal movement. So movement of the core of the body. And motor and interneurons that are located more laterally are actually responsible for movement of distal muscles, the muscles of the limbs. Okay? And this lateral medial and distal proximal organization is a fundamental parallel system or parallel organization that you will see across the entire set of descending pathways. Because in a way it allows us to actually control simultaneously both distal and axial movement. So from the brainstem, we are talking, there are three pathways that are related, relate information, delegate information to the spinal cord. There is the mid, and we're talking about medial system that reaches this medial part of the spinal cord. There is the lateral system that reaches the dorsolateral part of the intermediate zone, intermediate zone, and reaches distal muscles. And there is a third system, which we call the aminergic system, that actually provides very broad and diffuse innervation of spinal cord with neuromodulators, serotonin, noradrenaline, and so on and so forth. But generally, I mean, the systems from the brainstem, we're talking about medial, lateral, and aminergic systems. So the medial pathways contain the tectospinal from the tectum, the reticulospinal, and the vestibulospinal. And again, all these terminate on the medial part of the in the spinal cord. And the lateral pathways, we are talking only about one pathway, and that is the rubospinal pathway from the red nucleus to the spinal cord, and there it reaches the lateral aspects of the spinal cord, and where it actually affects muscles of the distal limb.
What about the cortical spinal?
So this is not from the brainstem. Now I'm talking only about the brainstem of the spine. Okay. So.
Sorry, can I ask you to use the microphone?
Sure. Okay, so, and this is just a list. I mean, we are not that, I mean, the pathways, the vestibulospinal, we are talking about an ipsilateral pathways. That is kind of, there is no crossing to the other side. And it actually, originates from the vestibular nucleus, and it's responsible for integrating or for descending integrated information about balance and posture. Because the vestibular nuclei, I mean, they receive information from the semicircular canal, and it's important, and they are important component in our ability to control balance and posture. The tectospinal is a contralateral pathways, and it originates from the superior colliculus. So the superior colliculus, I mean, will eventually innervate muscles of for eye movement. However, we also want to coordinate the eye movements with head movements, okay, and also possibly some hand movements. Or at least like. It's important that information from the superior colliculus will reach at least the cervical part of the spinal cord, where innervation of neck and upper limb proximal muscles is located, and the system actually is responsible for eye-head coordination, and in fact it's more than just the head coordination, because if we see, if we look at the fibers and the tectospinal pathways, we see that it innervates not only interneurons in the spinal cord, but also propriospinal neurons. These are spinal neurons that have very long axons that actually can affect multiple segments in the spinal cord. So the system actually has impact, not necessarily a local impact, but rather an impact that could actually span several segments. And this is true also for the vestibulospinal. So in generally, all the medial brainstem pathways, they innervate a medial part of the spinal cord. They are responsible for activating interneurons and motor neurons that are related for axial movement and proximal movement, and therefore they are not innervating in a very fine resolution elements in the spinal cord. The reticulospinal system is in fact the origin is from the reticular formation. This is a diffuse set of nuclei in the brainstem. This is the only pathway that can both excite and inhibit interneurons and motor neurons. It has a very important control in posture, although recent studies have suggested that it can affect neurons and interneurons and motor neurons that can actually innervate distal muscles. So it's not exclusively a proximal controlling system. It can also affect the muscles of the distal limbs, and it has very important. It actually integrates cortical. The reticular formation integrates information from the cortex and vestibular nuclei, and it has a very important pathways, cortical reticulospinal pathways that originate from M1 and premotor, that again can innervate, can affect neurons in the spinal cord, not only during movement but also during preparation of movement. Okay, so the system is in fact considered to be actually important in relaying cortical command downstream. But all these pathways have a major impact on medial part of the spinal cord. Yes?
What is the M plus L stand?
Medial and lateral. So there is the pathway, it can be subdivided into a medial part and a lateral part. Yeah. Both of them are part of the medial brainstem pathways, and both of them are ipsilateral. But it's just like subdivisions of the pathway itself. Yes?
All of these pathways have inputs from higher level hierarchies, or
Yeah,
some of them can
yeah.
start also here?
So all of them, no, there is no like starting point without a higher control. I mean, but all of them have like more like upstream control. It could be cortex, it could be the cerebellar, but they all kind of relay information from upper levels. Okay. And the lateral pathway, which is really more interesting in the context of control of voluntary movement, is the rubrospinal. So this is the rubrospinal tract. This is the contralateral tract, like the corticospinal. So it starts the red nucleus from one hemisphere controls spinal, the contralateral spinal circuitry. Okay, it's in the red nucleus. I don't know if Yossi already talked with you about cerebellum. So in the red nucleus, there are two divisions. There is the magnocellular and the parvocellular division. The magnocellular, as it sounds, contains really large cells. The parvocellular has a set of very dense and compact, high density cellular composition of very small neurons. And the rubrospinal tract is coming from, the origin is the magnocellular part, where the large cells are. And what is interesting is that with evolution, the relative size of the magnocellular part decreases. So in fact, it's kind of, in terms of the ratio between the magno and parvo, and also the actual ratio versus brain size, we see that the magnocellular part actually reaches its peak somewhere at the level of the cat, and from then on it becomes smaller and smaller, relatively smaller. And in fact, in human, this is only a very thin sheet of neurons that surrounds the parvocellular part of the red nucleus. So generally, the rubrospinal tract is considered to lose its importance in higher mammals, in primates, in apes, in humans, and we think that it is in fact that all the function of controlling voluntary control of distal movement that were located in the red nucleus migrated upstream to the motor cortex. So in cats, the motor cortex is not as important for controlling, for fractionating movement, controlling the subcomponents of movement. That's in the cat. The red nucleus in cat is very important for coordinating movement, for example. But in primates, this control of coordinated movement is actually located in the motor cortex. There is an expansion of motor cortical control of voluntary movements on the expense of the rubrospinal tract in lower level animals. But so the parvocellular part, so there are two parts in the red nucleus. There is the magnocellular that actually integrates information from the cerebellum and the cortex, motor cortex, and transmit it downstream. This is the magnocellular, and this is becoming smaller and less important with evolution. The other part of the red nucleus, which is the parvocellular, is in fact part of the cortical rubro-olivary pathways from the cortex to the red nucleus. From the cortex through the red nucleus to the cerebellum, this part is in fact became more important and increased in size. So the balance between, so one of the things that we see happen in primates compared to lower level animals, primates and above compared to lower level animals, is that systems like the cerebellum, the red nucleus, the basal ganglia, that used to have direct access to the spinal cord, in fact, lose their direct impact to the spinal cord, and they affect eventually motor cortical circuitry. So, for example, if we look at the cerebellum in mice and rats have a very important direct impact via the red nucleus to the spinal cord. However, in higher mammals, most of the cerebellar output goes through the motor cortex. And from the motor cortex, information descends downstream to the spinal cord. So instead of having multiple independent pathways that control spinal activity, everything goes through the motor cortex. And there are advantages and disadvantages to this arrangement. What could be the advantage?
More computation and more tuning.
Yes, exactly. And what could be the disadvantage?
Less precise.
Like if injuries or something happens.
Delay
Yes.
also
It could,
takes more time.
yeah. It could be that we cannot generate a very a fast, complex movement. Our ability to control movement in a fast way may be decreased, and we are more sensitive to injury. So mice, damage to the motor cortex has very little impact on their motor abilities. But in primates and humans, of course, any damage, even small damage to the motor cortex, produces permanent, to some extent, permanent motor deficits. Okay, so from the brainstem, we are talking about the medial pathways that reach the medial part of the spinal cord, and the single lateral pathways, the rubrospinal, that reaches interneurons and motor neurons that control distal limbs, but probably it has reduced importance in primates. Yes?
I'm not sure I understand the advantage of concentrating everything to the motor cortex.
So I think we can generate a more or we can have a better computation that takes into account many different inputs. So all the different afferents actually somehow, or the different plants comes to terminates at the motor cortex, and our computation actually can be better, right? Because we have more information at one level, especially the motor cortex, which is considered to be the computational aspect. If you're computing something very complicated, but there is another system that controls the pathways, that's kind of it's not going to work that well.
I want to say that too, but if we do make more complex and accurate movements, but I mean a cat has very
I agree.
much better movement or abilities than us. So
It has
fast movements, that the cat can jump very fast in a matter of seconds, things that right.
yeah, so that's
But cats have
to understand
more-
the advantage
yeah.
of moving.
so cats have very good control of balance and posture, right? I mean, they're pretty amazing. And they can have, but they cannot make independent figure movement. So they don't have a high resolution control of muscles. I would say they operate more in terms of muscle synergies, right? Global synergies. So they can, and their control over synergies, over these synergies is very precise. But they are limited first in the spectrum of movements they can perform, and they cannot have a high resolution control of single muscles as much as we do. So that's kind of okay. So if we compare the medial versus lateral, I mean these two sets of pathways, okay, are different both in the evolutionary stage where they appear. So the medial pathways are of course phylogenetically older. They mostly control balance and posture by controlling proximal and axial muscles, and because of this function, their termination pattern is very broad. They have very broad termination fields, because when we need to control posture and balance, we basically need to activate almost the entire sets, or the entire segments of the spinal cord, right? Because posture requires controlling leg and trunk and upper limb muscles at the same time. And therefore, the termination fields of these neurons, descending pathways, is very broad. The lateral pathways have a broader motor spectrum. They control reaching and object manipulation by controlling distal muscles. And as I said, the function of these pathways, the rubrospinal, which is a single lateral pathway, was probably overtaken by motor cortical areas. And we'll talk about it later. The last set of pathways that is interesting, in fact, and gained more recently, more interest, is the aminergic pathways. Because we are talking about descending pathways as transmitting information. But the aminergic pathways are not a part of an information channel, right? They don't really transmit specific information. They control, aminergic pathways control the excitability of spinal neurons and motor neurons, but they cannot activate postsynaptic cells, right? You cannot activate postsynaptic cells by putting serotonin or noradrenaline, but you control the level of excitability, how easy it is to reach a threshold for these cells. So we are talking.
So they are coherent inhibitory, or?
Sorry, no, they are. They contain noradrenaline and serotonin, and their impact can be excitatory or inhibitory. With this, yes. Serotonin can have excitatory or inhibitory impact depending on the postsynaptic cell and the specific receptors, right? So because you can have, these neuromodulators, they don't really operate via synapses. They operate via receptors, via different type, not necessarily via synapses. There are also synaptic contacts, but they can also operate, and that's why it's so difficult to really appreciate their impact, their postsynaptic impact, because it's not like you count synapses. They can have also operate via the membrane, receptors that are on the membrane. So we are talking about the cerebrospinal system that actually contains noradrenaline, starts from the locus ceruleus and the pontomedullary reticular formation, and it descends via the ventral part of the lateral column, and the raphe spinal system, which contains serotonin. The origin, of course, is the raphe nucleus and descends via the ventral and lateral column. Now, serotonin, at least, was shown to have a very important impact on the gain of motor neurons. So, if you look at the axons of the aminergic system, these axons, actually a single axon can make contact via almost the entire spinal cord. Okay, because again, we're talking about a modulatory system that changes the excitability level of the entire spinal cord. At least what we think is that the spinal system modulates sensory transmission in the dorsal horn. So serotonin can affect motor neurons, but it can also affect or gauge sensory information that arrives to the spinal cord. So I just want to show you what is the impact of serotonin. So motor units or motor neurons actually are very sensitive to application of serotonin. So what you can see here is a response of a cell to a current with and without serotonin. So you can see that this is actually the response in terms of the voltage of the cell. So we are actually injecting current in, and this is a slice preparation. We inject current, and we either put in the bath serotonin or not. And you can see that without serotonin, here is green, the response of the cell is subthreshold and kind of really follows the input that we give. However, if we put serotonin, the cell starts to fire. So it's more excitable, and the excitability is self-sustained. So even after the input was terminated, we shut down the input, the cell continues to fire in a self-sustaining manner. So what we think is happening, if we look at the gain of a motor neuron, okay, so this is the output to input relationship. We measure it in muscle force, and we measure it in synaptic input. We have, this is the gain as a function of changing gain as a function of concentration or levels of serotonin, and increasing the level of the serotonin actually increase the gain of the motor neuron. Now, why could this be important, or when do you think it should be important? This type of playing with the gain, or having like changing the gain of motor neurons and allowing a self-sustained firing. So, yes.
When there is some kind of danger and you need to escape.
Okay, that's okay. So you kind of then you just increase the threshold of the entire spinal cord, and you make your threshold much faster. Okay, and what other options?
No, I have a question. It's always to lower the threshold so there's more excitability, or it can happen the other way around?
So like well, if you think about serotonin level as a volume control, you can, if normally at rest there is a given rate of serotonin firing, of rough firing, you have always some level of serotonin, and then in the absence of serotonin, you decrease the level, and so it's like a volume control. You can think of it like that. Okay.
Control like fast movements.
Okay, that's one option. But like what? Okay, so one of the things, if you have to design a system, where would you put receptors for serotonin on motor neurons? Would it be proximal or distal muscles? Distal muscles. Any other ideas? You think proximal. So why do you think proximal?
Because they tend on the right, and also I think for distal movements we would need more fine control and also general.
Yeah. So this is true. The idea is that some parts of our body requires to have continuous muscular tone, and we don't necessarily want to have. Now, motor neurons is a cell that is very difficult to fire, right? How many synapses you have on the pyramidal cells in the cortex? a lot. Okay, 10,000, something like this. How many synapses we have on the motor neuron? 150,000. Okay, so it's like way more. I mean, it's like between 50 to 150. These are giant cells, and it's very difficult to have them reach threshold. You know, it's like so if you have to control like muscles that responsible for axial or for posture, you need the muscles to be continuously active, right? And you don't want to waste energy on a continuous motor command that will just say, okay, keep on firing, keep on firing, keep on firing. There is no information there, right? I mean, it's just like keep on firing all the time. You actually will design such a system.
No.
Okay. Yes.
Maybe continuing about inhibiting also instead of that.
Yes.
I think maybe when during sleep to prevent.
Yeah. Okay. Sleep is complicated. Okay. Sleep is complicated because we may have a specific set of inhibitory control, supraspinal inhibitory control, dedicated for sleep, to prevent that inhibits motor neurons in a very general manner. And it could be also, so I'm not so sure about the level of serotonin, but I'm sure it's also being modulated at that time. So we want to shut down, basically we want to buffer the muscles from our dreams and the central, the central activity during sleep, right? You want to buffer it. And there is a set of inhibitions that operates during sleep. But it's interesting, I don't know exactly the level of serotonin at this stage.
But in this case, when sleeping also, when you're in a bed, you never fall down even though you move. So there's kind of muscle contraction that you're moving in a certain way.
Still, but still the main characteristic of sleep is general atonia.
Yes.
So there is like, you see a mid drop in muscle tone during sleep. How come, well, we are still in bed, but, monkeys, they don't sleep in bed, right? They sleep on a tree. And, and they don't fall. I mean, at least not frequently. And it's kind of interesting how they manage to control this. And I think that part of the segregation of control of medial and lateral pathways allow us to control this system independently. So.
How we control that
That we won't fall during sleep? No, I don't know.
No, we do control that we don't do, we don't, I mean.
Yeah,
we
okay, well, that is a different.
Children, we don't.
Yeah.
Yeah. Not obvious.
No, it's not obvious at all. No, I think the kind of, but what happened exactly to the muscular control during sleep, that's a different field. I'm in the voluntary control of hand movement. So, no, I'm joking. But it's complicated, and other than the general atonia, but you are talking mostly about autonomic control, and when or like being able to wake up when things reach some threshold. That's another control. But the serotonin modulates excitability and is probably more important for axial and proximal muscles, where we want to play with the gain of the system more than with distal muscles. Okay, but what, in the context of voluntary control, what we are in the main pathway that is of interest is the pyramidal tract. And the pyramidal tract, this is just the pathway, you can see, and we know that complex and precise motor actions and voluntary actions actually depends on motor signals, motor cortical signals. We cannot really make any movement without a intact motor cortex. But the motor cortical areas can affect motor output either via the direct pathway, the pyramidal tract, which contains about 1 million fibers, or the indirect cortical brainstem pathways that contain about 20 times more axons. So most of the pathway, most of the information from the motor cortex goes through some further processing at the brainstem. Okay. So if we look at the direct pathway, so the indirect pathway is part of using the brainstem pathway, the cortico-reticular, cortico-rubral pathways. These are the most important parts. The direct pathways start from the motor cortex, goes through the internal capsule, make sense collaterals at the level of the medulla to cranial nerves, and at the level of the medullary pyramid. This is just the pyramid is kind of a structure. You've probably heard about that. Did you have a neuroanatomy? Some of it, What do you mean? Like, what do you mean? Some of it?
Some of us.
Some of you. Okay, I thought some of the neuroanatomy. You have. Okay, that's true too. Okay, so at the level of the medullary pyramid, the axons cross to the other side and give rise to the lateral corticospinal pathways and reach downstream interneurons and motor neurons. So, if we look, what is the composition of the structure? So, if we look at the spinal cord, ventral and dorsal, motor and sensory parts. If we look at these are motor cortex, premotor area, and sensory area. And although we tend to think about the corticospinal as a motor pathway, only 60% of the fibers are actually coming from the frontal lobe for motor areas. 40% of the corticospinal pathways is actually, the origin is sensory areas. And these sensory areas transmit information to the dorsal horn, where they are responsible for gating sensory information. The cortex is not passively receiving incoming information. It continuously controls the gain of these channels, of these sensory channels, and we can actually gate sensory information depending on the behavior. For example, when we make a movement, there is a suppression of sensory input from the skin. Okay? So when we make a movement, when you make a voluntary movement, there is, on one hand, there is a motor command to motor neurons and interneurons, and at the same time, there is suppression already at the level of the spinal cord of incoming sensory information. And why do we want to suppress it? Because
Distinguish between self-generated.
yeah, exactly. Because you learn about the reflex pathways, most of them trying to stabilize a state, right? We want to stabilize a state, but making voluntary movement is displacement from this state. So we are actually reducing the gain of the sensory flow, and in this way, sensory input or expected sensory input doesn't interfere with the control of movement. Okay? So 40% of the fibers in the pyramidal tract are from sensory areas. Another important myth is that this pathway is exclusively contralateral pathways, but in fact, only 75% of the pyramidal tract is contralateral, 25% of it are ipsilateral fibers from one hemisphere to the same side of the spinal cord. So which are the motor cortical areas that at least contains or are responsible for 60% of the input or the to the pyramidal tract? So this is the brain of humans, okay, right? So this is what what is this sulcus? The central sulcus, okay. So at least one person learned neuroanatomy, but this is the central sulcus, and the areas rostral to this sulcus are traditionally the motor area, primary motor cortex, area 4, premotor area, supplementary motor area, and then more frontal area. Eye movements are being controlled somewhere here. The posterior parts are sensory area. There is primary the somatosensory cortex, areas 3, 1, and 2, and these different areas actually process different aspects or different submodalities of somatosensation. And there is the posterior parietal cortex, area 5 and area 7, that are in fact very important in coordinating reach and grasp, okay? And they send direct information to the premotor areas. So these are the classical motor areas, but we consider area 5 and 7 also to be visual motor area. So visual areas that are related to movement, reach and grasp. In monkeys, because again most of the studies are being done in primates, we have very similar organization. Central, of course, it's not as complicated, but we have the primary motor cortex, the premotor ventral, the premotor dorsal, SMA, and then frontal ifield here, and prefrontal, different parts of prefrontal cortex. Okay. It's very hot here, right? I mean, it's kind of like I'm falling asleep. Yes.
It's about the somatosensory of
Yes.
the monkey. So you said it's also in the frontal part?
No.
I didn't.
Sorry.
So the integration should be similar I'm asking about the primate.
Yes.
So the integration is similar with the somatosensory?
Integration in what respect?
Like areas 5 and 7?
Yes. That's kind of most of these studies. I mean, yes, this is definitely.
Are based on
on primate. Yes. Yeah, I don't show it here, but I hope to have enough time to show it by next week. Okay, so again, we are talking about the ipsilateral and the contralateral corticospinal pathway, and the ipsilateral, which is the ventral corticospinal, originates in area 4 and area 6, motor and premotor cortex. It doesn't project to it doesn't have this contralateral projection. It's completely ipsilateral, and it sends information collateral to the medial brainstem pathways, and its termination is mostly on the medial part of the spinal cord. What type of neurons and what type of movements are being controlled by these part of motor neurons and interneuron? Proximal, axial, posture, and balance. Okay? And the lateral corticospinal is mostly for motor area 4, 6, but also areas 1, 2, and 3. And these actually have this pyramid decussation, and it reaches lateral part of the spinal cord where it controls distal movement. So again, this medial lateral, and or axial, proximal, and distal segregation exists also at the level of a single, the corticospinal pathway. And how it, okay, so we'll go now for a break. There is some discrepancy between my watch and this one, but so now this is, on average, it's 45 minutes, and we'll meet again after the break. אני כאן, כל היום אני כאן, ולא קצת פחות כן, want the slide? No, I will today. I'm sorry. Usually what happens, I modify the slide the night before I do. That's why I always, I don't upload it ahead of time, but I will upload this one and the last one of today. I'll send it to me.
Maki, I think, is the one that is
So, okay, so what is the source of the, we understand the termination of pyramidal tract neurons, we know about the pathway, but what is the origin? So the origin of the pyramidal tract are neurons, pyramidal tract, or not pyramidal, pyramidal cells, okay? The pyramidal tract neurons are pyramidal cells, but the names is from different reasons, right? It's not that the pyramidal tract is not because it's a pyramidal cell. The pyramidal cells that are actually project to the pyramidal tract are located in layer, which layer? 5, right? I mean, so you know this. I mean, layer 5 is where the actually, so in sensory areas, in yes, it is layer 5. Ah, that's how you know it. Okay, yeah. So you can read too. Okay, that's a good start. So in sensory areas, the dominant layer in sensory areas is layer 4, right? This is and it gives the granular look of the cortex and the granular cortex. In the motor cortex doesn't really contain motor areas, don't contain layer 4, or layer 4 is really redundant. And the largest layer is layer 5. Okay, so there is large layer 2, 3, and there is a large layer 5. There is barely no layer 4. And layer 5 actually contains neurons that project to all downstream elements: spinal cord, medulla, tectum, thalamus, red nucleus, striatum, okay, and some cortical. So this is the main output layers. And in these layer 5, we have, in the motor cortex, in the primary motor cortex, we have really, really large pyramidal cells because they need to maintain an axon that has to go all the way to the lumbar spinal cord. So in the primary motor cortex, there is a distinguished features of super large pyramidal cells that are called Beck cells, and in fact, histologically, this is the way that we distinguish between motor and premotor cortical areas. Okay. So, and these are the source for the pyramidal tract. Now, the pyramidal tract, through evolution, went through some modification, some changes, and there are two major changes that took place in the pyramidal tract, and this one of them is the increase in size, and the other one is the ventral shift. So what you see here, this is section from cervical spinal cord in different animals located at different levels of the evolutionary tree: opossum, cat, rhesus monkey, non-human primate, and an ape. And what you see, this is the gray matter, right, the butterfly. These are the number of fibers of the corticospinal tract, shown here in the white matter. And these are the terminations or the synapses that these fibers create. Okay? So you can see that as we go from opossum or to cat, for example, the number of corticospinal fibers is small, relatively, And the synapse they make is mostly at a dorsal and intermediate zone. So they don't make, the corticospinal tract in cats don't make direct contacts with motor neurons. However, if you look at rhesus monkey, first of all, the number of, the size of the pyramidal tract increased, but also the termination pattern shifted ventrally from dorsal side to more intermediate and some termination as the motor neuron pools. And indeed, at some point in evolution, there is the pyramidal tract changed its function from sensory gating, as we see here in opossum and to some extent in cats, to direct control of muscles, as we see here, and even more so in chimpanzee. So we have more contact. The motor cortex has direct contact with motor neurons. Okay. Now in rhesus, it's mostly wrist and finger muscles that are being directly controlled by the motor cortex. But as we go from rhesus higher to evolution, motor cortex control more proximal muscles. Okay? So this shift, the anatomical shift of the pyramidal tract, is correlated with increased dexterity in these animals. And dexterity, control of control of fingers. Yes, it's like dexterous. It's like when you can have very accurate finger. Okay. So now the termination field of these cortical motor neurona is rather large. This is a tracing of a single fiber, cortical motor neuronal fiber. This is the work from Shinoda that show that a single fiber, a single cortical motor neuronal fiber, can innervate several synergistic muscles. It's not necessarily a connection between one cortical cell and one muscle, but a single cortical cell can control a synergy, muscle synergy, and can control both motor neurons and interneurons. So it's a fine resolution control, but probably not at a single muscle level, but at a small synergy level. Okay? So now we can learn about the function of the corticospinal tract by looking at embryogenesis of the pathway. So if you take, this is the work that was done in kittens, okay, and kittens, little cats, and you can see that the pathway actually evolve after birth. The corticospinal pathways evolve after birth. And if you look at the cat that is 1 month old, this is what you see here. This is an inset of the spinal gray matter, and you can see 3 different corticospinal fibers. And you see that they have a very extensive arborization field, which overlaps. But if you look in adult, you can see that the fibers actually, that many collaterals actually were eliminated from the corticospinal termination field, and what appears are synaptic clusters, like here. So there is some acquired specificity of the corticospinal connectivity. With motor experience, there is a reshaping of the corticospinal connection, and some connections are being eliminated while others are being strengthened by the emergence of these synaptic clusters. And again, you can see in the immature spinal cord, the spinal cord of the immature cat, you can see that corticospinal termination go both contralaterally but invade also the ipsilateral side. You can see it here. But in the mature cat, there is a confinement of the corticospinal termination locally and enhancement of some synaptic contact. So, again, if we look at the depth, the spinal depth, this is the distribution of EPSPs. It's a field, basically, synaptic potential. You can see that the strength of connection, you stimulate in the motor cortex, and you measure the response in the spinal cord as a function of depth, and you can see that the response is very broad. It's not very strong, but it's very broad. And this is in the immature cat. In the mature cat, see the scales. The response is much stronger, right? It's almost more than 10 times stronger, but it's localized, spatially localized, okay? So this process of elimination and refinement and strengthening, this is a process that the corticospinal tract goes through by exposure to motor experience. Now, this is very different than the way sensory information terminates in the spinal cord. So axons from the periphery terminate in the spinal cord in a very precise manner, and this is based on chemotaxic process, right? And the connections are very precise, okay? And they are being finalized before birth, okay? So the immature cat has already mature spinal circuitry, but on top of it, there is emergence of corticospinal pathways that the way it is, the refinement of this pathway is experience dependent, okay? That's a very good question. Maybe some, but very little. If there is plasticity, it's mostly in the motor cortex. There is little plasticity. There are changes, but it's not. No, something happened. It's not like you know. Yeah, it's shocked. You know. All right, so maybe there might be, but the problem with spinal cord plasticity, it's not clear how it is controlled, you know, whether it's experience dependent. It's not like, in the motor cortex, it's a very, very robust phenomenon. I don't know what the functional implication of this, we'll talk about it later, but there is. But in the spinal level, in the corticospinal level, in a sense, there is a critical period, okay, for this connectivity, and after that, it's very difficult to change it. I don't know if it's possible at all. There are not a lot of experiments about that. But, okay, so if we look, the growth of layer 5 axons to the spinal gray matter is actually happens before birth and early postnatal stages. That's the actual growth of the pathways. However, the refinement and the elimination takes place postnatally in some critical period that can change depending on the animal. So for cat, it takes 2 months. For monkeys, 3 to 8 months, and in human, 1 to 2 years. And that's why, you know, kittens, when they are 1 month old, they can do fairly fancy things, and humans cannot. Most humans. And only after the full refinement of the corticospinal pathway, we can have, or the motor ability can develop, okay? But the actual movement and the exposure to movement and to the environment is critical for the proper refinement of these pathways. So you can see in these experiments that, again, were done in cats. If you block the motor cortex in one side, okay, so this is a normal development. In 1 month, there is a broad termination pattern of the corticospinal, and there is a bilateral representation, okay? So the yellow hemisphere there is a contralateral bias, but it also has some ipsilateral representation. After 2 months, normally, there is like a almost exclusive ipsilateral representation, and there is a refinement of determination. Okay, this is normally what happens. However, when we block activity, in motor cortex in one side, you can see that in 1 month the development is fairly normal. Okay, so the early stages, the actual development of the termination is normal. However, the refinement process is impaired in a way that the active hemisphere takes over the ipsilateral side that should normally be devoted for the what is now inactive. Okay, so so here, I mean, the block is only during the first month. Okay, so it's a specific. It's not like a continuous damage, but it's a temporary block during the time where refinement should take place. Okay, but the results are permanent. So what type of experiment this should remind you? In visual system.
The one with the stripe?
Yeah, the stripe, and the one that you block closure, eye closure, and this ocular dominance impairment. So in a way, the system is similar in this. If activity is critical for the normal development of the corticospinal pathway.
And what is the behavioral phenotype of
Of the kitten? Yes, that's a good question. There are impairments, but I don't know. I don't have the information. But you can go there and read. Okay. So, but in cats, the entire system relies on cortical spinal connectivity, and only interneurons have direct impact to motor neurons. But in primates and humans, there is the appearance of the corticomotor neuronal system, and this appearance actually has a very important functional significance, because people found evolutionary correlation between first the emergence of these corticomotor neurons and our ability to perform independent movement of the fingers. So a precise grip, the ability to hold objects with the thumb and the forefinger. It's like this is a precise grip, and these cats cannot do this. Okay, and the fact that we are able to activate separately each finger, right? Cats or lower animals can only have like a extension or flexion of the entire fingers. They cannot control fingers independently. And there was a large. This is happens in primates, but also raccoons, for some reason, have this ability for independent finger movements together with corticomotor neuronal. Yes.
Is it because the wiring in the hand itself is different with humans and cats, or just only the wiring in the brain?
Just the brain.
So in the hand, like the neurons,
So there are.
therefore every finger the same amount.
So how the muscles for the cats? I don't know about the cat, but I think they do have. Okay, also primates, for example, don't have like independent muscles that extensor for each finger by itself. But still, you don't have to have independent muscles in order to be able to independently control, because in the muscles you can also have segregation. You can have motor units for each single fingers, etc., etc. I don't know about cat anatomy well enough, but I'll show you an example that actually demonstrates this correlation. We know that by correlating function and anatomy, that only animals that can have cortical motor neuronal pathways have this independent finger movement. The other thing is we know that this is not the structure of the hand. So this is the hand of the macaque, which is the normal, or sort of the primates that are being used for studies, humans, okay? And these are two examples of a squirrel monkey and a cebus, capuchin monkey. Both of them have very similar organization of muscles and a very similar hand. However, the cebus is a very is a well-known tool user and has a very a fine control of finger manipulation. The squirrel monkey doesn't have the same capabilities. Again, despite the fact that the muscle organization is very similar. But if you look at the spinal cord, the spinal termination in the cebus, you can see that it has a very pronounced termination at the motor neuron pools. So it has a lot of cortical motor neuronal connection. And this is very different than the cebus. So you see this is T1 of the cebus monkey. So it's not exactly the same scale, I kind of, but you see that there is hardly any termination in the motor neuron pools. So the number of cortical motor neurons is much smaller. Yes?
If I understand well from this, you don't need to change like the actual muscles in order to gain a new function.
Yeah.
It's more like the motor units that get to the muscle.
No, it's the command that goes to the motor unit.
It's more in the wiring up. You don't need.
Yeah.
Evolutionary doesn't need to change anything in order to
No.
gain a new.
No, the ability to use tools is like is not dependent on the involvement of specific muscles. It's a computational infrastructure change, not the muscles. Okay, so and more recently, people have suggested, and this is the work of Peter Strick, that in fact the primary motor cortex should not be viewed, at least in primates and possibly humans, the primary motor cortex should not be viewed as a single homogeneous structure, but you can divide it to two parts. And the first part, these are, okay, so this is like the central sulcus, and this is the flattening of the map, of the motor cortical map. And you can see the location, this is the anatomy, and this is the evoked movement. So you stimulate here in the motor cortex, and you evoke different type of movement, of finger, elbow, and shoulders, here again. And you look here, and you see that just deep in the sulcus, if you look at the central sulcus, deep in the sulcus, there is enhanced concentration of cortical motor neuronal cells. So what Peter Strick suggested is, in fact, with evolution, we develop a new part or unique part of the motor cortex where most of the cortical motor neuronal system are located, and this part is actually increasing size with evolution. So for us humans, this is a more major part of the primary motor cortex. And what he called it, this is the new M1. And the new M1 contains most of the cortical motor neuronal cells that innervate motor neurons and to some extent interneurons, while the old M1 has mostly impact. And the old M1 is on the lateral surface of the motor cortex. It has mostly impact on interneurons. And why is it important? It's important for the question of where in the motor system the motor command is being dictated at the level of single muscles, right? Because if we ignore new M1 and all the motor cortex is like this and only small fraction will go directly to motor neuron, it may suggest that the motor command that comes from the motor cortex is mostly high-level abstract command, and the translation to muscle-based command will take place here. However, if we have this system as the major component of the primary motor cortex, we may expect that already at the cortical level, the command will be specified at muscle-based coordinates. Okay? Because every movement that we make has abstract aspect to it. So I want to move my hand to this target. I can define this command in a very abstract way by moving to this target, or I can define it, okay, this muscle will be activated this much, and this muscle this much, and so on and so forth. And depending in some way on the organization of the system, we may expect this translation from abstract form to muscle-specific command to take place either at low level or high level. Okay.
Can you explain the figure again? I didn't understand.
The figure itself. Okay. So these are okay. How this experiment is being done? What Peter Strick is doing is injecting rabies virus to the muscle. Now the rabies actually go and it jumps synaptic contact. So okay, so this is actually a good time to kind of explain some of the methodological flaws of this approach. So recently, okay, so the way he's doing it, he's like, how do you know that this is he said, okay, I'm waiting 1 day. If I do the perfusion after 1 day, the virus can only jump 1 station. If I wait 2 days, the virus can jump 2 stations. And if I wait 20 days, the virus can jump, I don't know, the entire brain. Okay, so he's using time, expected time, in order to trace the circuitry. More recently, there are recent studies, I don't know, that actually modify the virus, and using some CRE recombinant modification, the virus can only jump 1 station. But that's not what he's using, because this cannot be done in monkeys. This is work that was done in monkeys. The CRE recombinant can only be done in mice. But in mice, you don't have any corticomotor neuronal, so there's no point to this. In monkeys, you don't have the CRE recombinant, but the system is interesting. So depending what you are more interested to enhance your tools or enhance your understanding of the motor system in humans, for example. So you inject the virus here. You wait 1 day, you get only a kind of you only find these trace of the virus at the spinal level. You wait 48 hours, you find, and this is what he found. So this is counting the virus, this rabies virus localization in the motor cortex, and this is just the density.
But I didn't get the direction.
Okay. So I'm like, I'm not even answering your question. Okay. This is the central sulcus.
Okay.
So, so if you look, this is the brain. This is the brain, right? This is the central sulcus, and this is the arcuate. So you take the central, you take this, and you flatten it, right? So this is the central sulcus here. Sorry? This is rostrum, and this is This is area 4, but this is the bottom of the sulcus, and this is area 3A. So this is sensory area.
I don't get what we see here. That is more than the muscles we all know.
No, but this is all corticomotor neuronal connection. So what he found is that most of the connections, if you inject to a muscle in the shoulder, are actually very near the bottom of the sulcus. So what is the problem? That when we record electrophysiology, physiologically, we usually miss these parts, right? How does the sulcus, this is the cortex, right? This part is here. And this is sort of, so it's something like this, right? We usually it's difficult to get all the way here. It's easy to be missed, and you don't know where you are. I mean, really, it's like you go and it's the cortex never ends. You go in and more and more and more, and still, like, you know, you go for. So it's easier. There is a bias in our recording toward this part, and our understanding of the motor system mostly comes from studying what Peter Stricketlis calls the old M1, and he suggests that in fact, if you look here, you'll find more cortical motor neurons, and you may find different coordinate frame of the motor command if you look in the right place. So, this clear this kind of stuff? Okay.
So in lower animals, you don't have the fine map of each muscle?
In lower animals,
Sorry, like that.
wow, no.
Mice going down.
In mice, the maps are very. There is a general distal and proximal segregation, but there are no maps in the motor cortex. Also in the motor cortex, at least most of the motor cortex, there is no like muscle-based map, because if, okay, you inject in one muscle, you see, usually what you see if you look at the entire motor cortex, you see colonies. So areas, different areas in the motor cortex that project to that muscle. Then you project to different muscles, you see other colonies, but there is overlap. So there is no, like, it's not a singular a map of one muscle, right? If this looks like that, or here, there might be some segregation because it's a shoulder, elbow, finger, but it's only like 3 muscles. I mean, if you go and inject the entire, it will be a mess. You won't see such a precise map, okay? Okay. Yes.
All the new, are they also using brain or
Sorry?
are they two interpretations of
No.
the cortices, or
These are 2 parts, coexist, but the question is it like, first of all, we want to know evolutionary. I mean, is it possible that we are moving, that the new M1 will take over the old M1? I mean, does it take over in humans? We don't really know this. The other thing is, what are the relationship, the computational relationship? It could be that in parallel we send 2 commands downstream. One is to the level of interneurons, and the other one to the level of motor neurons. And these are 2 motor commands that are being simultaneously sent downstream. So for example, you can think, I don't know if, did Matti tell you about the neural integrator idea of in the eye movement system? Sorry? Yeah. So there is a neural integrator, this idea that a velocity-based command is being translated to position-based command downstream. So you can think that in fact this sends a velocity-based command, and here this is already a position-based command. So this sort of, you have a parallel, you don't need a serial integrator. It's not, in the absence of the new M1, you'll have a velocity that is being integrated into position that is being sent to muscles. But these 2 pathways can send the velocity and the position simultaneously. Okay?
Which one is the velocity?
This will be a transient command, and this will be a sustained, a muscle-based. So position-based, or it's not position, it's a force-based command, should be, this is what the muscle can read, right? Muscle cannot read velocity, cannot integrate in itself. Or I mean, they can, but to only a small extent. Is this clear? It's like kind of...
like a different theory? Or was the impression that you...
It's a huge argument. It's not a theory. It's an argument. It's like that's kind of a... But I will talk about it soon when I talk about motor cortex. What is the coordinate frame of the motor command that is being sent downstream? Is it muscle-based or space-based. Okay, so, and there are evidence, and of course you can see where Peter Strick here and some other people are think differently. This is kind of an ongoing debate. But the anatomy is clear. I mean, in a sense, it's not kind of. There is some anatomical evidence about the connection of CM cells. Okay. So now, what happens when the motor cortex, or when the cortex cannot send information to the spinal cord? So we can think of a complete spinal cord injury, right? I mean, so, you know, how many of you are riding motorbikes? You, of all people? I can't believe this. So it's like, okay. So one of the, a common injury, because they have a helmet, so the helmet actually protects the brain, but below the helmet level you can get spinal cord injury, which is complete interruption of the entire cortical spinal, or the entire connection between the supraspinal and the spinal cord. And in response to this insult, there are a series of events that can tell us something about how important the connection is. And the first thing is that the first day you have a complete areflexia or hyperreflexia, which is because due to the loss of descending facilitation. So descending information acts or enhance or activate, excite spinal elements, and in the absence of these input, you get the entire system, the excitability level of the system drops, and the tonus, the muscle tone, is very, very low. So this is the first day after the injury. Then, within 1 to 3 days, reflexes started to build up. The system, the spinal system, basically lost all sources of descending input, which includes the the brainstem pathways, the cortical pathways, the aminergic pathways. So all these inputs are gone. But there is some kind of homeostatic response of the spinal circuitry. And at first, there is a supersensitivity due to the denervation, which is responsible for the initial reflex return. So there is some, you pinch, or you use a small needle, you pinch the skin, and there is a response of the limb. And but within short period of time, this return of reflex actually develops into hyperreflexia, and that's because of synaptic growth and hypersensitivity, hyperreflexia, and spasticity due to in a kind of spinal mechanism that try to compensate for the loss of the innervation. And most of the major source of problems are those, as I showed you before, in the presence of serotonin, we can get enhancement of reflex gain. And this is due to a persistent inward currents. These are specific currents that are being, these are channels that are opened by serotonin. And these are persistent inward currents that cause depolarization in the presence of serotonin. However, after the injury, these persistent inward currents develop, or they open in a tonic, uncontrolled manner. So the entire gain of motor neurons is enhanced.
Wait, where does the serotonin come from?
No, there is no serotonin. This is sort of a response to the loss of the serotonin. Due to some mechanism that we still don't understand, those channels are being expressed independent of serotonin, and they are responsible for a shift of the motor neuron gain to a high level.
So they become
Exactly. And so this change in gain caused spinal cord patient to become spastic. And spasm means that there is an exaggerated response, motor response, to even slight or previously subthreshold sensory stimulation. So the entire posture is is impaired. You know, people with spinal cord injury can become spastic, and which means that they are very rigid in their muscle, in the posture, because of this enhanced muscle tone. Okay.
Do they aware of it? I mean, when they react to...
Well, they don't sense it. They don't sense it. There is no sensation, but they observe it.
They just observe it.
Yeah, they have no control over it. No, because you lose the entire sensory control of below the injury. This is in a complete spinal cord injury. Yes.
And why is there a spinal cord?
So there is some homeostatic response of cells. They lost part of the input, so they sort of, the system compensates on it by kind of having new synapses grow, or enhancing the strength of existing synapses. It seems like this is sort of a homeostatic mechanism that is not fully understood.
And there is no way to achieve some...
So there is a way to fight spasticity, which is a major problem for these patients, by using serotonin antagonists. Actually, they, for some reason, can relieve part of this spastic behavior or phenomenon.
Does it hurt them? I mean, if they don't sense it, what's the problem with having...
It can damage. There is, yeah, no, but there are also like these. First of all, I mean, sometimes there is like a tremor. It takes a lot of energy, you know. And also this fixed posture is not like is not healthy for the bone and for the muscles, you know. It's like kind of it may generate this problem in the skeleton. It can injure, and because they cannot feel it, it in itself can cause injury. They can't feel it. I mean, that can actually exaggerate, you know. Okay, but this is of course in the absence of complete this is in a complete spinal cord injury, but we are interested. Okay, we say that the pyramidal tract is very important for voluntary control of movement. So the question is, what happens when there is a specific injury in the pyramidal tract? Now, these type of injuries do not occur spontaneously. I mean, there is no like a known injury that causes. So, in this set of experiments that were made by Kuipers, I studied for many years the pyramidal tract. What he did is actually a complete bilateral cut in the pyramidal tract at the level of the medullary pyramid. Because at the level of the pyramid, the pyramidal tract is really exposed. I mean, it's very superficial. So he actually cut it, and these is monkeys, and he measured, you know, he observed what are the phenotype of these monkeys where the pyramidal tract is cut. So the acute result is a severe muscle weakness. That's the first few days. There is a general muscle weakness. But with time, the monkey recovers, and in fact, many of the motor capabilities are completely restored. There is a balance and posture are restored. The monkey can climb, you know, can indicate. It's very difficult to see that there is any problem. It can climb, it can walk, it can jump around. It's a little bit slower, but the main deficit is that precision grip is lost, and also isolated distal movement. So the monkey cannot make these independent finger movements, cannot have this fine control of actions. You can see here. The monkey needs, this is a Culver board, so we take a board, we put small, in those holes, we put food, small pieces of food, and the monkey needs to grab it. Normally the monkey can do it very well using precision grip, but in impaired monkeys, you can see that he cannot use this fine finger manipulation to retrieve the food. Now we think that the indirect pathways can actually compensate for many of the motor behavior that are required for the normal day-to-day activity of the monkey. However, there is no backup system for the fine control of fingers, because this system, the fine control of finger manipulation, is exclusively controlled for by the corticospinal tract, and especially the cortical motor neuronal connection. So, although normally the pyramidal tract takes part of all these normal activities, there is a backup system via the indirect pathways. Okay, so on Sunday we will meet again and we'll talk about computation in the motor cortex and how motor commands are being actually generated and controlled. So I'll see you on Sunday.